Hello everyone. I'm here to present our work titled Morphotectonics, Slope Stability, and Paleostress Studies from the Bhagirathi River section, published in Journal of Structural Geology. This study brings together structural geology, geomorphology, and geotechnical analysis to better understand tectonic activity and slope instability in Bhagirathi River Valley, Lesser Himalaya. These findings collectively add depth to our understanding of the tectonic, geomorphic, and geotechnical behavior in this sector of the Himalaya. In this multidisciplinary approach, Western Himalaya is characterized by intense tectonic activity and frequent landslides. The Bhagirathi River section presents a unique opportunity to study how recent deformation, weak rock masses, and paleostress regimes control landscape evolution. In our multidisciplinary approach, we integrate morphometric indicators, slope stability parameters, and fault slip data to create a comprehensive tectonic and hazard model for the region. This slide presents the geological map of the Bhagirathi River basin. It clearly highlights and emphasizes lithological complexity and fault orientations derived from published seismic and tectonic datasets. The sterionets clearly demonstrate through field and analytical data fault planes and associated lineations used to infer past stress regimes, setting the structural context for our analyses. The lithotectonic succession of the Lesser Himalaya, based on Biswas et al., 2022, forms the foundation of our stratigraphic interpretation. Highlighted in green are the units from which we collected field data, targeting zones affected by major thrusts like the Tons, Tarasu, and Singuni thrusts. Our workflow includes morphometric analysis and subwatersheds prioritization using the TOPSIS model, field and lab-based slope stability assessments using RMR and soil tests, and paleostress analysis using slicken lines processed in WindTensor to reconstruct regional stress regimes. 21 subwatersheds were delineated across the Bhagirathi Valley using hydrological tools. The TOPSIS ranking model was applied to morphometric parameters to assess tectonic activity. SWS 3, 9, 12, and 17 were identified as most active due to their proximity to thrusts. This table summarizes the parameters used in morphotectonic analysis, such as form factor, hypersymmetric integral, and asymmetry factor. Each parameter captures terrain shape, uplift rates, and drainage asymmetry, providing quantitative inputs to the TOPSIS model. Here we present the computed morphometric values for each subwatershed. High RC, FF, and AF values correlate with areas of rapid incision and tilt, while hypersymmetric curves provide maturity indicators. These outputs feed directly into watershed ranking. Using the R-square-based model, we ranked watersheds based on tectonic activity potential. Higher R-square values provide significant indications that stronger structure control on landscape. Bold values clearly highlight and emphasize the most sensitive subwatersheds, reaffirming our earlier observations. SL index variations in subwatersheds 3, 9, 12, and 17 clearly demonstrate, through field and analytical data, anomalies near tectonic structures, such as the South Tibetan Detachment, Vaikrita, Munsiare, and Tons thrust. Sharp SL jumps mark zones of active uplift and fault reactivation. The morphometric analysis clearly demonstrate through field and analytical data that subwatersheds intersecting major thrusts exhibit enhanced deformation. Combining SL index and TOPSIS results provide confirmation through both qualitative and quantitative evidences that tectonics remain the primary landscape shaping force in the Bhagirathi Basin. Slope stability was evaluated using RMR and SMR from 11 locations. Soil samples were tested for shear strength, cohesion, and moisture. The field data was collected from zones K1, K2, and K3, each with unique lithological and structural setups. Sterionets from LM3 and LM4 clearly demonstrate through field and analytical data planar failures governed by joints J1 and J2. Foliation and slope orientations intersect unfavorably, increasing failure risk. The rocks, primarily slate, are slightly weathered, leading to poor cohesion. At LM7, a combination of wedge and planar failures was observed, controlled by J0 and J1 intersection. LM9 exhibited planar failure along foliation planes. Both locations underscore how joint geometry directly influences failure mode. Geotechnical classification clearly demonstrate through field and analytical data. Most slopes fall under bad to very bad stability, with SMR values below 20. This is especially true for locations L5, L7, and L9. Clearly highlight and emphasize the role of poor rock mass conditions and unfavorable slope joint orientation. Lab results clearly demonstrate through field and analytical data. Gravelly sand textures with low cohesion and variable moisture contents. Direct shear tests provide confirmation through both qualitative and quantitative evidence. Low shear strength, making these slopes vulnerable, especially after monsoon infiltration. In our multidisciplinary approach, we gathered fault plane data and slicken lines from quartzite and slate exposures. These were processed using the right dihedron method in wind tensor. Each slicken line provided orientation data used to determine local stress tensors. In this slide, we clearly demonstrate through field and analytical data case the field documentation of slickened sides, polished, striated surfaces on fault planes formed due to movement along fractures. These geological features were photographed and measured across K1, K2, and K3 zones. In our multidisciplinary approach, we focused on identifying lineation types such as ST3 and ST5, following Doblas, 1998, and slickolite planes, as per Twissin-Moores, 2006. The orientation of these slicken lines provides vital inputs for paleostress modeling, as they reflect the slip direction of past fault movements. Such observations, when analyzed with wind tensor, help us interpret the dominant stress regimes that have shaped this segment of the Himalaya. Paleostress analysis across all zones revealed three dominant regimes: northeast-southwest extension, R equals 0.25, north-northeast, south-southwest compression, R equals 2.69, and a strike-slip regime, R equals 1.48. This lent robust support to our hypothesis, multi-stage tectonic reactivation, linked to Himalayan arc dynamics. In K1, normal faults provide significant indications that pure extension along 16 degrees to 196 degrees, with R equals 0.48. Reverse faults clearly demonstrates through field and analytical data, compression along 30 degrees to 110 degrees. Provide confirmation through both qualitative and quantitative evidencing dual-phase deformation in this zone. K2 data clearly demonstrates through field and analytical data all three regimes: dash extension, compression, and strike slip. This zone is heavily deformed, consistent with stress rotation and arc parallel shear deformation, indicating the most active tectonic environment. Though fault data is sparse, K3 still reveals extension along 11 degrees to 1950 degrees, and compression along 70 degrees to 250 degrees, with R values indicating a mixed regime. Our analytical results are consistent with nearby K2 zone trends. This table consolidates stress orientations and R values for all zones. The coexistence of compressional, extensional, and strike-slip stress regimes reflects the tectonic complexity of the Bhagirathi Valley. Our study concludes that tectonic segmentation is evident along key thrusts like Darasu, Tons, and Singuni thrusts. Unstable slopes are driven by weak rocks and unfavorable joint settings. Geomechanical properties like low cohesion soils worsen failure potential. And paleostress regimes provide confirmation through both qualitative and quantitative evidence multiphase deformation across the basin. Thank you. For further correspondence or collaboration, please reach out at given emails. These findings collectively add depth to our understanding of the tectonic, geomorphic, and geotechnical behavior in this sector of the Himalaya.